My name is Filip Hlobik, and I'm a second-year PhD student at the Comenius University in Bratislava. And today I will talk to you about our Tau-Herculids meteor shower outburst observed by our AMOS cameras from Arizona. Firstly, let's quickly talk about the Comet 73P Schwassmann-Wachmann. It is a periodic Jupiter family comet with a period of roughly 5.44 years. And it was discovered in 1930 by Schwassmann-Wachmann in Hamburg Observatory in Bregedorf, I think, Germany, and was lost for a lot of years, almost 50, until it was recovered back in 1979. And since its discovery by, it was linked to the Tau-Herculids meteor shower by Nakamura et al. In 1930, who observed an outburst in that year. Then, in its 1995 perihelion return, an unexpected outburst in brightness happened in September of that year, which resulted, or which was caused by a breakup of the comet near the sun. And then later in December, at least 4 fragments were observed. One of them was this one, fragment B. And then later in 2006 and all of its subsequent perihelion returns, more fragments were observed. These are pictures from 2006 of many more of these fragments. And this massive breakup of the comet inspired scientists and researchers to model some kind of meteor shower outburst that could happen, maybe even up to meteor storm. And one of those predictions predicted an outburst in 2022. Except that the Tau-Herculids is an established shower with a number of 61 in the IAU MDC database, and is normally of very low activity. But there were those outburst predictions, which predicted a maximum at the end of May 2022, on the 31st of May, with the best observing locations in North America, as we have seen in the previous presentation. This was also the motivation for the Slovak expedition to come to America. And so the Slovak expedition visited Arizona, and there were 15 different cameras at three locations. One at the double R gas trench near Benson, Arizona, one at Chiricahua Astronomy Complex, and one outside the map at Mount Graham Observatory. The data we have used in this presentation come from these 2 AMOS cameras, which were located at the double R gas trench and the Chiricahua Astronomy Complex. Here we can see the used AMOS cameras here in the field and here in our workshop at Modra Observatory with its enclosure taken off. And it's the same camera as our stationary AMOS cameras without the opening enclosure. And it consists of a fisheye lens, image intensifier, another lens, and a camera sensor. It has a field of view of 180 degrees by 140 degrees with a resolution of 1600 by 1200 pixels, shooting at 20 frames per second, and with limiting magnitudes of +5 for stars and +4 for moving objects. Moving on to some results from the maximum night of the 31st of May, 2022. Both of the stations were running for roughly 8 hours from 3 to 11 UT. The Doubler station captured 403 meteors. The Chiricahua station captured a bit more at 479 meteors. Those are all single station, and we assume that most of them are Tau-Herculids, even though it hasn't been checked yet. And here we can see at the graph the effective hourly rates of the meteors, which were corrected for the position or zenithal distance of the radiant. And we can see, as was reported by other reports, that the activity happened, or the peak of the activity happened between 4:30 and 5 a.m. or UT, right here. Out of these 403 and 479 meteors, we were able to find, or we were able to pair 165 meteors to get double station measurements using our proprietary software Meteor trajectory, or MT in short. And using the criterion of Southworth and Hawkins with the value of 0.2, we found 110 Tau-Herculids in these 165 double station meteors. We also plotted the effective hourly rates for these double station meteors. And once again, the maximum happened at the expected time, but we may see some lower rates in comparison with those with these last graph, which is caused by the smaller field of view due to the double station configuration. The next thing we've done on these double station meteorites were that we looked at the magnitudes and the population index, and we calculated the population index using two different ways. One of which was a tool by the Western Meteor Physics Group by Vida et al. And using this method, we found a population index of 5.01, which is quite large, implying prevalence or dominance of dimmer meteors. And our magnitude range was from negative 2.17. This was our brightest double station Tau-Herculid, up to 2.5. The other method for calculating the population index was much simpler. It was based on plotting the cumulative counts in logarithmic scale and trying our best to fit this, let's say, linear part of data. And then the slope of this curve is our population index, which came at 3.91, which is still on the higher side of other reports, as we can see, but is not so far away from the data by Peter Janskens. Moving on to the radiant, we can see that most of these are very compact, with the mean radiant and the median radiant being very close to each other, with some outliers around. And zooming on to this compact area, we can compare with other published data, and we can see that our median radiant was very close, once again, to the data published by Peter Janskens, and in the right ascension was quite close to the data by Cotton et al. From this year. And lastly, we can compare the orbits The thicker orange line is the orbit of 73P, and these are all the close orbits we found using the Southward-Hawkins criterion. So in summary, we have processed the data from our AMOS cameras in Arizona, the single and double station activities. We've calculated the population index in 2 different ways, suggesting a prevalence in dimmer meteors. We calculated the radiant and orbital elements, and what's next? As I've said, there are 15 cameras in total, so there's still a lot of data to go through, and it will take some time. Thank you.